Hello. Right, in this one we're going to look at resistance, what causes it and what changes it, and how we add them all up, etc, etc, etc. So resistance is basically a factor affecting whether electrons move through a substance. Now, the electrons are actually moving are in an orbital which is essentially dissociated. It's not really connected to any of the atoms, any of the nucleuses. Because they're entirely overlapping, because the metal atoms are so close together. But still, the atomic nucleuses do have an effect. And where they have an effect is with this wonderful animation, which of course isn't on the screen. The warm wire at the bottom, the little pluses, are supposed to be jumping up and down and making it difficult for the negatives to go through. Which is why when you've done this, you should have a quick flick through the PowerPoint, which is on the WordPress file, and just make sure that the animations make some sense to you. But I suppose the most important thing about this is that the resistance depends on certain factors. How hot the wire is, resistance goes up with temperature. The material, the better the material, the closer the atoms, the lower the resistance. Gold is one of the best. The length, the longer it is, the more resistance. The cross-sectional area, the narrower it is, the greater the resistance. So you can decrease resistance by increasing the cross-sectional area. And this is all true for a metallic conductor, as some of you may have already remembered, because I've done it before and some of you haven't. In a semiconductor, the reverse happens. As the temperature increases, the resistance goes down because there's more things to carry, more electron-hole pairs. But in a metal, if you increase the temperature, you increase the resistance. And this is the experiment you would do to prove same. Again, you have glycerol, a thermometer, and something which you're measuring the resistance of. The small symbol on the right there is enough to, there you are, see, that's all you need for an ohm meter. You don't have to label it because it's an agreed symbol. So you're measuring the resistance of that piece of wire wrapped around a frame. It's in glycerol, which has a low specific heat capacity, so that there's a good chance that the temperature of the thermometer and the temperature of the piece of wire are the same, because they spread their heat very easily. And basically, there you have it. Also, it's an insulator, which also helps the whole process. But the main thing is the low specific heat capacity. So that is your experiment. You simply vary the temperature by pouring in hot water and letting it cool very slowly, and you measure the resistance at different temperatures, and you plot a graph. Nice, easy. That's the type of graph you get. Do it slowly, wait, which is always with heat experiments. Okay, so cross-sectional area, length, they have a huge effect. Cross-sectional area, obviously, that's the inverse, which means as the area goes up, the resistance goes down, and length, which is proportional, which means as the resistance goes up, the length goes up, or as the length goes up, the resistance goes up. It's all there. But we don't remember any of this. Not a word of it has to be remembered. I introduced it, certainly at that speed, because I want to introduce you to this formula, which you will find in the logbook. It's the resistivity formula. Resistivity, sometimes written resistivity like that, is basically the resistance times the cross-sectional area over the length. And what you're basically saying is that just when we were doing heat, where different materials have different specific heat capacities, different materials have different resistivities, meaning that gold has a different resistivity to iron. So if you make something out of gold and you know its dimensions, its cross-sectional area and its length, you can have a pretty good guess within sort of like an order of magnitude of its exact resistance. And if the gold is pure and tested, you can work it out absolutely exactly. That is resistivity. And iron would need a different size to produce the same resistance. Now, we measure resistivity with this rather pleasant experiment where we very carefully string a piece of wire, usually nichrome again, between two retort stands so that the wire is tight. This is so you get a true length, and also so that you don't get any kinks or bends or anything like that. So you measure the length between 2 points and the resistance between 2 points using an ohm meter. Remember, you say you measure the length with a meter rule and you measure the resistance with an ohm meter. There's the meter rule or meter stick down there on the diagram. We also have a micrometer. Now, a micrometer measures the diameter of the wire. Now, you have to do this in at least 10 places and find the average. Because of the kinks and bends in any wire, it's not going to have a uniform diameter all the way down, and you have to find it in 10 different places and find the average. The other thing is you also have to do it at different angles, so not just different places, but different angles. And then finding the average diameter, you substitute it into this equation. Here's the diameter used to find area, and this is the formula we were talking about earlier. I've just used some bizarre colours to try and ram it home. But of course, as you know, these things are in the logbook. So we don't want any kinks, no kinking, no kinkiness, don't want any kinks, not even Lola, nothing like that. We want to ensure the wire is straight, and we take the diameter at different points and different angles and find the average. Aha! So now we move on to working out the formulas for resistors in series and parallel. You have to know this derivation. They are very simple, and they're based on what I was saying the other day, i.e. that voltage adds up around a series circuit and that current adds up in a parallel circuit. Now, because of the one on the left, the series, we can use Ohm's law in both cases to find the formula for adding up the resistances. Here is it being done in a series circuit. You see, as I said, all the voltages add up, and V equals IR, that is Ohm's law. But, as I also said to you, current is the same everywhere in the circuit. So, if I write it down for each component, including the total, that the current times the total resistance is equal to the current times resistance 1, blah, 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 just converting them from voltage, I can cancel out the current and I'm left with a simple formula that we simply add up the resistors, as you would expect. Now, it's not quite as easily in parallel because we're adding up the currents. And if we adjust Ohm's law for current, we get voltage over resistance. So we have to write it in this form. But again, I did tell you that the voltage across each component in a parallel circuit is the same. So if it's the same, it can be cancelled. So we end up with the formula 1 over RT, 1 over R1, 1 over R2, 1 over R3. So those rather simple proofs don't take an awful lot of memory. What does take a little bit of time is explaining this idea of the Wheatstone Bridge. It's a devised by Mr. Wheatstone, who's up there in the top left-hand corner, just making an appearance, slightly more smiling than Mr. Ohm, who's only about 10 years afterwards that picture was taken. Temperature control, mainly used for. Fail-safe devices used to be used in burglar alarms. Measure of unknown resistance is what we really use it for. The idea is that you set up this bridge balance with R1, R2, R3 and R4, and you connect between B and D a very sensitive galvanometer. And when it reads 0, then the Wheatstone Bridge is considered balanced. And in that case, you can have R1 over R2 is equal to R3 over R4, just reading them 1, 2, 3, 4 in the way that they are there. Now, this formula is in the logbook and we don't have to remember it. If you're giving a Wheatstone Bridge question, they cannot ask a really difficult one. They're usually very simple and the formula is in the logbook. And it's almost impossible to muck up if you do it properly. The thing to remember is that there has to be a connection across there. And the galvanometer must show 0. That's called the null point, When the galvanometer shows 0 and there is no current flowing between B and D, then it's considered balanced. So, what does electric current actually do? It heats things up, it makes chemical changes, and it creates a magnetic field. And we're going to look at each of those now. First of all, we're going to look at the chemical effect, which is the easiest thing to explain. Basically, electricity flowing in a liquid moves not just electrons, but it moves ions, charged particles, charged atoms, ions, which have lost or gained an electron. And they move backwards and forwards in the liquid, and they are in fact the movement of current. Now, Electroplating relies entirely on this and is the only example we really need to use. So we plate things with this chemical effect. Now it's also used in the purifying of metals, making oxygen and hydrogen, and the making of electrolytic capacitors, which are luckily beyond the scope of this course. But if you want to cover something with another metal to make it pretty, then you need the chemical effect. You need these ions moving about. So, now, copper, which is the one we investigate, has got active electrodes, so it obeys Ohm's law. Can you hear what I said about Ohm's law? A straight line through the origin? There it is. This is not a straight line through the origin. This is what's called inert electrodes. Those of you who have ever seen the voltameter, which is the thing which separates hydrogen and oxygen so that you can make those little beepy noises with the hydrogen and relight a glowing splint, if you've ever done those experiments, then that's done with platinum placed in acidified water. Now, because the platinum doesn't take place in the reaction, it doesn't actually, nothing happens to it, it's still the same at the end as the beginning, we say it's inert. Whereas the copper, which partially dissolves into the liquid, that's called active. So where you've got an active electrode, you get Ohm's law. Where you've got a passive or inert one, you don't. What carries charge? Medium. Right. Carrier. Let's look at each one in turn. These are quite important. In a solid, particularly a metal, electrons. Electrons carry the charge. In a liquid of any type, the ions, charged ions. And fascinatingly, in a gas, both electrons and ions carry the charge. But the other one that is not present, and I will scratch in at the bottom, is of course the semis. A semiconductor, it's electrons and holes. Now, you know my feeling on this. Holes don't carry anything. They're just the absence of electrons. But that's the thing that you're supposed to write down. So that's why I'm sketching it in rather than writing it in hard copy. In a semiconductor, electrons and holes. So if we go back to where we were talking about earlier, resistance increases in temperature in a metal. So this is a metal. The resistance is going up with temperature. This is a semiconductor. In a semiconductor, the resistance decreases with temperature because more hole pairs are being liberated by the heat, which allows more conduction. Now, the thing that's confused by this is, of course, scale. I reckon the maximum scale of resistance here would probably be in the order of maybe 100 ohms. The resistance here starts at about 1,000,000 ohms. So the scales are slightly different. The resistance in a semiconductor is obviously much greater. That's why it's called a semiconductor. Aha! Fuses. Fuses are to prevent fires. What are they not to prevent? They're not to prevent electrocution. Fuses melt to prevent too large a current going into the device, which will cause it to catch fire. Modern fuses are often miniature circuit breakers these days, but this is one which is just a simple wire which is so thin that it'll heat up when it gets to more than 5 amps and melt, or simply. Now, which fuse would you use depends on this formula over here. P equals IV. The power is current times voltage. Now, this is a very important formula which is sadly not used very often enough in any textbooks, and one of the reasons I don't use a textbook for any of these is there's so many admissions like this. An iPod charger uses 200 watts and is plugged into the mains at 230. What fuse plug should you use? Well, you've got the power, you've got the voltage, you're looking for the current, because fuses are always rated in current. So you simply use P equals IV to find the current which is actually flowing at the point it's charging, and then you need a fuse which is just slightly bigger, so that if it exceeds 1 amp, the fuse will melt so that your phone won't be damaged. Of course, nearly all plugs contain fuses far too big and comparatively useless. Other safety features, well, a lot on the continent. They still use double insulation, which means they wrap everything twice in plastic. And there's also the so-called residual current device, which detects the difference between the live and the neutral connections in your plug, literally the brown and the blue. And if the connection is greater than a certain value, usually 30 milliamps is the one we use in Ireland. So when the difference in current is greater than that, it switches it off, because there can't be any good reason for it to be bigger than 30 milliamps. If it's bigger than 30 milliamps, something nasty has happened, time to turn off. On your right, you see the residual current device. Now, you can see the difference in the bar. Can you see that? Most fuses are a simple switch. In a residual current device, you have a little bar, and that bar indicates what it is. You might only have one or two in the house. You possibly have two if you have an electric shower and it's been wired in the last 10 years. Otherwise, you possibly only have one. These are very effective devices. One working one is enough for any house, but there's no harm in doubling up the safety ever, really, is there? So, what does cause electrocution and what prevents it if not the fuse? Well, what prevents it is earth. Everything metallic within an electrical device should be connected to the earth, literally to the ground. That's what the earth is. They mean the planet. When they say earth, they mean the earth, not earth. It's just, bad case studies, lack of a definite article. So every piece of the case which you could touch and which could be metal and which could carry electricity has to be connected to the earth, the yellow and brown wire. If this happens, any fault which leaks current into the casing will be carried away to earth. Now, at this point, the carry will go so quickly, the electricity will flow to earth so quickly that almost immediately the fuse will melt, causing the article to stop. Now, I say almost immediately, but not quick enough to stop it hurting you. So, if you want not to be hurt, then what you have to do is have an earth, because it will flow to earth instantly and not to you. Only then will the fuse melt and prevent any further damage, prevent fires and things like that. But you have to have the earthing in to prevent electrocution. Wiring the plug. Stare, look. Neutral, blue. Earth, green and... What did I say? Brown. Did I say brown and... Anyway, green and yellow. Green and yellow earth. Brown is the live wire. Brown is the live wire, which is... it's the live wire because it's connected to the fuse. That's how you know it's the live wire. And there you have the double insulation. Insulation on each of the wires and insulation on the wire itself. Okay, 2 questions here. One of them involves the Wheatstone Bridge. I'll let you work your way through these. They're not too bad. Just remember what I said about B and D. There has to be a galvanometer between B and D. There. And when that galvanometer reads 0, that is when it's balanced. Here the galvanometer is shown. That's the symbol for galvanometer, little arrow. And again, nice little question 12 here. I think this might be 12C. I actually can't remember. But whatever question it is from 2014. And it's a happy little problem. And I think you'll find it easy enough. So that ends the second part of electricity.